Welcome back. Let us resume our discussion on the zeros and look at the circuit techniques to mitigate the effect of that zero. So, as we have seen the origin of this problem, we are having this zero because of this dual path from the input to the output. So, the origin of the problem is that we are having a signal path from the output of the first stage going to the output of the second stage through this dual path. One is through this capacitor and another one through this MOSFET, and their phase are falling opposite at certain frequency and exactly cancelling out at the zero frequency, and that is what is resulting in this term in the numerator. So, if we can eliminate one of these two paths, then we can get rid of this problem. That is one strategy, one possible scheme used to compensate this kind of circuit, and in order to do that we can think of inserting some component over here which can block the second path. So, basically we want to eliminate the signal transmission from the input to the output through one of the path. Of course, this is not that path because this is the amplification path, we do not want to disturb this path, but this is an undesirable path through which the signal is propagating from the input of the second stage to the output of the second stage, and if we can block that, then we can succeed in our stabilization. So, in order to do that, we can insert a buffer, maybe a unity gain buffer, with input at the final output and the output connected to the CC. So, this is once again my second stage. I have inserted a unity gain buffer between the output and the input, and this is coming from the output of the first stage. I am not drawing that. So, here if I look at the overall functionality, because of this buffer, it is a unidirectional buffer. You can think of it as a voltage follower or even a simple common drain amplifier with gain close to unity. So, in that case, the common drain buffer or a unity gain buffer is going to transmit signals from the input to the output, but it does not allow passage of any signal from the output to the input. Therefore, it is going to block any signal transmission from the input to the output side. Therefore, the overall signal transmission now becomes now has only single path. You have basically blocked the second path. Now, does it still have the Miller effect coming into picture? Yes, because the gain is remaining same. All you need for the Miller effect and the Miller compensation is that the gain between or gain within the signal or voltage level at the other end of the capacitor with respect to the first end should be sufficiently high, and that is not changing much because of this unity gain capacitor, unity gain amplifier, because the gain from the output to this point is 1, therefore, the Miller effect remains intact. Therefore, this is able to compensate the overall two stage response by still exploiting the Miller effect and getting the CC multiplied by large number. At the same time, it is also blocking the second path and hence helping us in achieving the overall cancellation of the zero. Now, in order to implement this particular zero, what are the in order to implement this particular amplifier, as I said, the simplest strategy involved is to use a common drain amplifier. So, we can think of inserting a common drain amplifier. So, in that case our circuit will look like you can have another bias point over here, and this particular point goes to CC. So, this is one particular scheme where the overall output impedance of this stage is given by 1 upon GM of this transistor, which can be made to be relatively low. But once again, when we are trying to incorporate this stage and trying to make the GM lower, it is going to add additional power consumption in this particular branch, because it will need sufficient bias current to have a large GM. So, that the output impedance of this stage is sufficiently low and it is acting like a good common drain buffer. In this analysis, if we assume that the overall output impedance of this buffer is very small, then we do not have any additional pole coming into picture, because if I assume that the output port of this amplifier is having almost 0 impedance, then basically the overall resistance the equivalent resistance seen by this CC at this particular terminal is almost close to 0. As a result, it does not lead to any additional pole. But if the impedance is not sufficiently small, if it is relatively higher or comparable to the RO of the MOSFET, in that case it can create problems, and once again it can lead to additional poles coming over here, because you can imagine that ultimately this point it is going to provide some R out of this common drain buffer or the unity gain buffer, and if this R out is very small, it does not lead to any additional pole, but you are not ensuring this to be very small, then once again it will introduce additional pole and then further complicate your analysis. Now, in a application where you have power constraint, like in our case we are looking for a front end amplifier or a biomedical application where you are having many channels and therefore bias current is an important factor. I do not want to burn a lot of bias current in this stage to reduce the R out. One of the other option is that you increase the W by L of this MOSFET, so that you can have a much smaller GM just by scaling the W by L, because GM depends upon both the products root under W by L times ID. So, that is another option, but that also has its limit, because ultimately you will end up increasing the area of this MOSFET, and as a result the channel area will increase. So, we know that we are, apart from the power, we also have a severe constraint on area in this particular application, because we are going to have many such channels catering to different electrodes, and we do not want to make any of the component too large to meet any of our design specification. So, both from the point of view of power as well as area, having this particular scheme can create issues. It can violate our area constraint per channel or power constraint per channel also. The alternate method can be that you add a voltage follower over here, which can be constructed with the help of a negative feedback amplifier, relatively low gain negative feedback amplifier, without having too much constraint of gain or linearity. So, we can construct a voltage follower using a simple single stage amplifier. And all the better if we apply another common drain stage after this, then you have a basically have a positive output over here. With respect to that, if you increase this particular signal, the output goes high and the final output goes high, and the negative output over here, and therefore I can connect these two. You can have the negative feedback over here, and as a result we know that this particular circuit, the overall impedance for a voltage follower is going to be small. This is what we are trying to implement. You have the V in over here, and you are trying to have a V out, and we know that this particular combination is a shunt series combination. You are having shunt at the series shunt combination, where you have a series combination at the output and shunt at the series at the input and shunt at the output. So, basically you are sampling the output voltage and applying it at the negative terminal. So, it is in series with the input signal. So, at the input side you have series combination, output you are just probing the voltage with a shunt connection, and therefore, and the beta factor we say is unity for the voltage follower configuration. And in order to find out the open loop impedance and hence the closed loop impedance, we know that we can just put an open circuit over here, because looking from the input port of the feedback network, I have a series connection at the output point. So, I can open circuit it, and looking at the output port of the feedback network, the other terminal is shunt circuit. So, I can just short circuit it or put in an AC ground. This is the equivalent open loop circuit corresponding to the voltage follower, and now I know the output impedance for this particular stage. If I am applying a common drain, R out becomes approximately equal to 1 upon Gm of the second stage, which is the common drain stage, and beta is 1, and whatever is the gain of the overall two stage is our overall open loop gain. Therefore, my closed loop gain or closed loop output impedance in this case, we know is going to be the open loop output impedance, which is 1 upon Gm divided by 1 plus A beta. Beta is 1, and the A is basically the A of this overall stage, which is of the order of Gm RO by 2. So, we can get a very small impedance if you are using a voltage follower buffer constituted of this differential amplifier and the common drain stage. And remember here, the response or the frequency response bandwidth of this particular stage should be within the or larger than the bandwidth of the overall differential amplifier, because the signal over here should be able to follow the main input signal, otherwise you will not get the commensurate mirror multiplication. So, this signal should be able to follow the input as well. So, we cannot afford to make this buffer having lower bandwidth as compared to the main amplifier. For the common mode feedback, we discussed a condition where we are only looking for the DC biasing part. And so, therefore, even if we make the common mode feedback circuit very slow, if we make the error amplifier of the common mode feedback very low bandwidth, it does not hurt the overall differential response. But here, since this is a part of the differential operation, we need this particular buffer amplifier also to have sufficient bandwidth close to the main amplifier. And one of the good point over here is that we do not need a very precise feedback factor and hence a very high gain for this particular buffer. All we need is a sufficiently low input output impedance, and for that we need to just have sufficient gain, so that the overall output impedance looking into the output terminal of this buffer is sufficiently lower as compared to the impedances provided by the output stages of our amplifier. So, if the output stage is providing impedance of say RO by 2, the output impedance of this buffer, if we are able to make it sufficiently lower than that, as evident from this expression, we are happy about it. We do not need to necessarily make this GM-RO too high to have any precise gain or closed loop feedback operation. That is not the purpose of this circuit. The purpose of this circuit is just to have sufficiently low output impedance at this point while providing almost unity gain. And to do that, we can relax the gain requirement over here. So, rather than targeting a GM-RO of few hundreds as we would do for the normal amplifier, here we can go for few tens and still get sufficiently low output impedance, because it is going to divide the 1 upon GM by that few tens further and going to reduce the output impedance over here. So, by this method we will be able to relax the gain requirement of this stage, and therefore, we can trade off with the bandwidth with the similar amount of bias current or maybe a fraction of bias current used for the main amplifier. We can achieve similar bandwidth at the cost of lower gain and still achieve low output impedance and a good buffer functionality for this particular unit, so that the effect of 0 is getting eliminated. So, this is one particular technique which we can employ in our design to use to arrive at the cancellation or elimination of 0. Now, let us look at the second one. Before we go, any question on this part? So, let us look at another common technique through which we can also cancel out the effect of the 0 by modifying this compensation path, and that basically involves insertion of a nulling resistor in series with the CC. So, once again I have the second stage, I have just inserted another nulling resistor RZ in series with CC, and therefore, I once again need to analyze the expression for V out in terms of the V in over here. And to do that, once again I will revisit my previous analysis where I had used two parallel paths and arrived at the expression for the output in terms of the V in. So, I am going to repeat that. Only thing is I have inserted an RZ in series with the CC. So, here once again I can write down the expression for V out as the superposition of the two paths. So, let us take the first path. So, this will be minus GM times V times the overall parallel combination of the small signal resistance at this point and the impedance provided by this path. So, the overall small signal impedance at this point provided by the PMOS and NMOS, once again I am calling it say R and R in parallel with the series combination of Cc and Rz. So, R in parallel combination with Cc plus Rz. This is the first path again, and the second path, which is again going to take into consideration the path through Cc and Rz. So, there once again while considering the second path, we are going to assume that the MOSFET gate is at AC ground. We do not have any signal applied over here, and the signal is propagating only through this path, and as a result I have the voltage division coming between the Cc Rz combination and the effective R at this point. So, once again I have the voltage division between R at this point and the combination of Cc 1 upon SCC plus Rz. So, we can try to solve this and look at the overall expression. One upon SCC plus plus Rz plus V times R upon R plus 1 upon SCC plus Rz, and I can once again take out some factors as common. So, V R and R and you have GM 1 upon SCC plus Rz plus 1 coming over here. So, this is the overall expression we can see, and once again I can simplify it a little bit further, and you have the other term as it is coming over here. Now, looking at the above expression, if I want to eliminate this 0 coming in the numerator, for that if I make this Rz equal to Gm. So, suppose in this expression if I set Rz equal to Gm, then this will cancel out with this factor 1, and you will be left with only the 1 upon SCC term over here, which will again be cancelled out with this SCC term coming over here. So, if I set Rz equal to 1 upon Gm, so this Gm is basically the Gm of the second stage. So, I should call it Gm2. If I set Rz equal to 1 upon Gm2, then I can basically cancel out this factor, I can eliminate the effect of this factor. So, in that case the only term that will be left in the numerator is 1 upon SCC, which is getting cancelled once again over here. So, this is another way, by inserting this nulling resistor Rz and setting its value equal to 1 upon Gm2, I can effectively eliminate the effect of the 0 coming because of this path, and hence have a much stable response. Now, the problem here is the value of Rz to be chosen and how robust this combination can be. So, we know that this Rz is a passive element which is which can be relatively well defined with plus minus 10% accuracy. However, Gm is not a very well defined quantity, it can vary significantly more widely. So, you can have plus minus 50% or even 100% change in the Gm. So, if you are in simulation, you are setting up this value of Gm to be 10 to the power of minus 4. In the actual design, you may get a value which is 100% or 2x or 50% of that. So, you can have a wide range in the values of Gm that you get over here after fabrication, and therefore, if you are trying to set this Rz equal to 1 upon Gm2 in fabrication in simulation, it is not necessary that after fabrication also you will get exact matching values Rz equal to 1 upon Gm2, and hence you will be able to cancel out the zeros. So, we need to make sure using some techniques that the matching between this Rz and the Gm2 is pretty accurate and independent of process and temperature. So, to that extent we can try to define the overall Gm of this MOSFET with the help of another biasing scheme, where the Gm of this itself becomes proportional to this Rz. So, if we make sure that the Gm of this particular device is proportional to RZ, then once again we can have a good matching between these two. So, that is what we are going to see, one particular method using which we can make the GM of the PMOS proportional to RZ very briefly. So, that incorporates a current reference circuit that we have not implemented yet in our design. We will very briefly visit that and try to see that how it can help us in establishing a GM which is controlled by the RZ or is proportional to the RZ, so that the cancellation can be much more robust. So, to do that, the scheme employed is that we can use a PMOS current reference we will be looking into this circuit in a little bit more detail, and in this particular circuit, if this is an R value which is being used, this is not a connection. So, in this particular circuit, if this is the R value, we can show that the biasing current that we get out of this I bias is proportional to 1 upon R square. So, that solution requires equating the current through this NMOS and PMOS and solving for the value of the current. So, we will be using this reference circuit later, and we will be looking at the detailed analysis of this particular block. And in this particular circuit, the bias current provided by the reference branch is proportional to 1 upon R square, and if we can apply this bias current for this output transistor M6, we can make sure that the bias current flowing in M6 is also proportional to 1 upon R square, and we know that the GM of the M6 is going to be proportional to IB. Therefore, GM of M6 can be made proportional to IB, and through that we can have a well defined matching between RZ and M6. All we need to do is that this RZ needs to be matched with this R that we are putting in the reference generation circuit. And as we have discussed earlier, matching of two passive components is very much feasible in integrated circuit. So, if you are trying to match two R values or two C values which are passive component, they can be very well matched. So, I can have these two resistance well matched. As a result, the RZ that we are having in the compensation branch, it is determining the bias current of the M6, and the M6 GM therefore is proportional to RZ, and by appropriate sizing we can ensure that the matching between RZ and the GM is very well controlled, and it is much less dependent upon process and temperature, and through that this cancellation can be made effective over a wide range of temperature and process variations, and through that we can ensure that the overall zero cancellation is achieved across process variation. So, this is another scheme that can be employed for the overall elimination of the zero in the circuit. Any question before we proceed further on the two schemes that we discussed for zero elimination?
So, what about noise in RZ?
RZ in general, we are having it is in the shunt path once again, and it is in the second stage. So, if we look at the overall amplifier, the noise is dominated by the first stage, and this is appearing at the second stage. So, that basically suppresses its effect on the overall output noise. So, and moreover, it is providing something similar to a shunt feedback, just like we have for the main amplifier. There also we have discussed that if the feedback resistor RZ or RF that we had in the op amp that is having a shunt configuration, the current mixed by that at the previous stage is relatively small. As a result, it is not going to have significant impact. And once again, we will revisit that noise analysis while we discuss the transistor level noise analysis, and there also we will try to once again justify a little bit more detailed analysis that the RZ appearing in the shunt feedback does not significantly corrupt the input signal or does not significantly add to the noise of the amplifier. So, here also if we see, ultimately this is a shunt configuration. Output is sensing using a shunt connection, V out is being sensed, so shunt, and at the input side you are again mixing current. So, it's although it is the entire scheme is voltage to voltage converter, but the feedback, whenever the feedback signal is mixed at the same terminal as the input quantity, we have a shunt at the input also. So, again we have a scheme which is similar to what we had in the op amp, and we use that large RF to bias the input node. So something similar over here. So in the simulation exercises also you can try out both these methods and try to see the effect of 0 on the overall phase response. So I'll try to frame a problem where you will be able to observe the 0 a little bit more prominently, and then you may be asked to use one of these two methods to cancel the 0 and get a better phase margin. So this two-stage op amp is again one very versatile block that you may be required to use at different stages in the overall design. So you have the front-end amplifier, you have the second stage amplifier, which is going to be probably a programmable gain amplifier. Beyond that you have filters, you may have ADCs. So this two-stage op amp can be pretty handy in building all these different blocks, the front-end amplifier, the filters, even in the ADC. If you are using certain topologies, you may be using this kind of amplifier. Therefore, we are spending some more time in looking at the analysis. So far we have seen the DC biasing point, we have looked at the frequency response, stability, etc. And the other part that is supposed to be addressed is the noise analysis, which is also going to play an important role in sizing of these transistors in our amplifier. So the next part that we are going to look at is going to be noise analysis of this two-stage amplifier. And as I just pointed out, the noise analysis essentially boils down to the low noise design of the first stage, because that is the most crucial stage. If you are having a high gain amplifier, we are targeting say 10 to the power of 4, 10 to the power of 5 gain from the open loop. There we assume that the first stage is having at least few hundreds of gain. So the noise contribution of the first stage is going to be dominant. So all we have to do in noise minimization is to make sure that the noise of the first stage, that is the differential pair, is minimized by appropriate sizing consideration. So that is what we are going to look at next, and determine the sizing considerations to minimize the noise contribution of the differential pair. Once this is complete, then we can go towards transistor level design and try to arrive at the transistor sizes analytically, considering high level design specification that we had for the amplifier. So whatever we are doing here, the frequency response or the noise analysis, ultimately similar concepts will be applicable elsewhere also. Even if you are using other amplifier topologies, like one of the target is to look at folded cascode topologies, where we do not have this problem of 0. We do not need to have Miller compensation. There we have another scheme which is called dominant pole compensation, which is inherently stable, does not give the 0 in the overall response. So we will be looking at an alternate topology also, but the overall concepts remain similar. You have to look at the frequency compensation, you have to make sure that you are using a 45-degree phase margin by inserting capacitances at proper point, and make sure that whatever compensation etc. you are doing, it is robust enough, it is not failing at different process and temperatures. So that is another important point. Apart from that, whatever we do in the noise analysis part or DC biasing part, the similar concepts apply in other circuit topologies also. So folded cascode is another very handy structure which can be employed in building different functional blocks. So there also we will be looking at similar analysis. So once we have gone through these steps, probably we can apply similar things to the folded cascode structure that we will be taking up for analysis after this, and start our discussion on noise analysis of the two-stage amplifier.